How are you all doing this morning?
Well, doing all right.
Doing okay. All right. For any of you who are willing to volunteer anything, how did you feel about the exam?
I felt pretty good about it. I felt like it was pretty similar to the review and like all the stuff we did. I mean, I didn't feel terrible.
Okay, that's good. Not feeling terrible is I guess a good start. Anybody else care to say anything?
I somehow still almost ran out of time. I don't know how that happened, but
Okay. Um, so I'll have to figure out something to that end. Did anybody else? I can see that some people took like 2 hours and 29 minutes, 2 hours and 28 minutes to take the test. Others managed to do it in like an hour and 30 minutes. Typically speaking, the people who took a little bit longer typically did a little bit better. But that isn't always the case. I think somebody in the chat said that they also ran into an experience of running out of time. And we got two people in the chat saying they feel not great, but that it is their fault. Okay. So I have not done the full-on analytics for the exam yet. So what I usually do is go through and calculate the minimum score, the maximum score, and the mean and all that kind of good stuff. And then I go through question by question and see how many students got it right versus how many students got it wrong to make sure that there isn't any questions wherein the correct response percentage is, say, if it's less than a third, I typically look at the problem again and make sure that I didn't make some dumb mistake, because that absolutely happens. And in the event that I did make a dumb mistake, and so like the correct answer wasn't available at all to you guys, I will award full credit for all of the options on that particular problem. So I'll have to go back through it and check those things. But like right now, I can see that for the students that took the exam at 10 o'clock in the morning, the average score was a 61, which is a little low. For the students who took it at, gosh, what time is this? 1 p.m. The average score was a 53, so that's less than great for sure. For the students that took it at, I think 4 p.m., the average score was a 74, which is actually pretty legit. That's kind of what I'm looking for. And then for the students that took it at 7 p.m., the average score is a 48. So out of the 4 time slots, really only one grouping hit where I was expecting. So let's assume for a moment that I didn't make any mistakes on the exam, which is a large assumption. What could I be doing better to help you prepare for the next test?
At the end of each chapter, if you could put up problems that are very like characteristic of what the exam is going to be like, where if we can go over those problems, practice on them, we'll be sure we understand like nodal analysis or mesh analysis. That would really help at the end of each section.
Okay, so instead of putting up like the old exams, kind of break those old exams down into different sections for the type of questions that I could ask for each topic. Is that a fair assessment of what you're asking for?
Yes, sir.
Okay. Any other thoughts or suggestions?
I mean, I felt like just the exams, like in my experience, like normally a lot of teachers don't do that. They don't give out older tests, like especially the tests that you gave us, which being so recent. I mean, you had a test from 2019 and 2020. I felt like that really resembled the test that we just took pretty well. So I mean, but maybe like a few problems here and there at the end of each section, but I felt like just giving that practice test really kind of prepared me the most. That's really all I studied. I worked through it and just kind of broke the problems down piece by piece.
Okay.
I would agree.
Alrighty. So I'll definitely. I think I'm going to do effectively a combination of what you guys have suggested, which actually boils down to kind of what the first person was saying, where I'm going to take tests from or problems from old tests. I might do it for more than 2 tests, but kind of try to organize them in such a way that they're representative of that specific lecture's materials, so that you'll have an idea of kind of exactly the questions that I would ask for that particular portion. With regards to the timing, I mean, I did take 10 questions off the test, so I'm not really sure what else I can do there. At least I can't think of anything. Do you guys have any suggestions other than make it easy?
I would personally say, for me at least, drawing them out is what took the time. Like,
Yeah,
I probably had, if honestly, I probably had 10 or 15 minutes just in drawing the problems out for me to see them on paper.
yeah, I definitely understand. Like my intent was for you guys to be able to finish this exam in roughly an hour and 45 minutes or so, and so those extra 45 minutes were for you to be able to, you know, draw things and take your time. But I might have, I might need to restructure things in such a way to where, like, I use the same circuit for like 3 or 4 problems or 3 or 4 questions, so that, you know, you're not drawing as many circuits, if that makes sense. Any other thoughts?
I feel that the reason I ran out of time personally is, well, I'm bad at time management, and drawing the circuits definitely did take a lot longer than I expected, because I was a little less than halfway through and I looked down and, oh crap, I have an hour left, because I was drawing out the circuits the whole time, and I had to like start hurrying, and I think that kind of played a role.
For sure, yeah. Well, seeing that timer, like, to me, whenever I had a test and there was a timer up, that always stressed me out more so than not knowing how much I had left, to be honest. Like, that ticking clock always mentally got to me when I had to take exams. So I will. I don't know. So I have to be careful about how I say it. I have no problem, like, let's say for exam 2, I made a 25 question test of similar difficulty to this one. I don't have any problem giving you guys 3 hours to take the exam whatsoever. I just don't want to get feedback to go to my academic director or dean saying, I'm giving you guys 3-hour tests, and effectively I don't want to get myself in trouble by being nice to you and somebody interpreting it in the wrong way. So I think what I can do, I will try to, or I will allow you to take 3 hours for the next test, so that there's even more time for you to redraw the circuits, and I'll try to lower the number of circuits that you have to redraw. And I think that might take care of that. But I want to be very clear, and I know I said it during the review session, these tests are in no way, shape, or form designed to take more than 2 hours. The extra time is literally to allow you to spend plenty of time redrawing the circuits correctly and then being able to do your analysis. Because you're in an odd position taking the class online that you have to redraw everything, whereas if you were taking it in person, you wouldn't. And so I definitely have to accommodate that need. And if I need to give you more time to do a better job of that, then that's okay by me. Any other thoughts or anything?
When will the grades be posted to Moodle?
So I have one student who is having some technical difficulties. I watched their Respondus video and all that kind of stuff. And so I'm going to let them make up a different version of the exam than the one that they took. Once they finish, I will release all of the raw stuff. So that will probably be later today. And then I hope to, by the end of the extended weekend, go through and look at all of the problems where the student responses percentage was lower than I had anticipated. And so you might see some slight grade adjustments over the weekend. But your raw scores as is, I would anticipate having them up by close of business today. Anything else? All right, well, we're going to talk about op amps for a bit today. I think I'm going to try to keep it kind of short because I'm expecting a phone call to go pick up my mom from the hospital in Shreveport. So as soon as I get that, I'm going to bounce, but I'm going to try to keep things nice and breezy for today anyway, because I feel like I've stressed you out enough with your test. So,
Appreciate that.
yeah.
When's that next mini lab, dude? Just curious.
They're all going to be due at the end of the quarter, but I feel like I forgot to upload some stuff. So I will probably take care of that on Monday or Tuesday as well. I'll get a couple of them up because they're going to be in a little bit of a jumbled order. The op amp mini lab is usually mini lab 7 or 8, and I think it'll be like your 4th or 5th one because of the way that I'm doing things. But I'll get off my ass and get those mini labs uploaded soon. I might just literally do all of them over this weekend and then just put them all up and tell you what material they go with, and that might be better. I'm very forgetful, unfortunately. All right. I'm sharing my that is not the color I want. All right, this thing is giving me an error, so I'm going to have to close it out and restart. I apologize. There is engineering paper. There we go. Let me remove all these old notes. There we go. Start on page 1. Okay, sorry about that. All right, so I'm actually going to open up another file here real quick to show you guys what the internal structure of an op amp looks like. It isn't particularly important to this class per se, but it'll be a pretty good explanation of why we're going to approach it the way we're going to approach it. So if I scroll down here to, I think, page 7. Nope. There we go. Can you guys all see this terribly large and crazy looking circuit?
Yeah.
Yeah.
Yeah. So this is what an actual op amp is. And actually, this is a functional block diagram, which means this is a simplified version of an operational amplifier. And we're told that it contains 22 transistors, which we know absolutely nothing about, 11 resistors, 1 diode, which we know nothing about, and 1 capacitor. And so it would not be unreasonable for you guys to think, gosh, this seems really, really complicated. Why are we going to analyze it? Well, despite the complexity of this guy, it actually obeys just a couple of very specific rules that make the analysis very, very easy. Okay. So in our circuits, we are going to represent an operational amplifier with the following symbol. It's going to be a triangle, which is the general symbol for an amplifier. And the operational amplifier is what's called a differential amplifier, meaning that it can take 2 different input signals. So I'm going to denote one of the inputs with a plus sign. So we have an input terminal here associated with the plus sign. This is what's called the non-inverting input. We're going to have an input associated with a minus sign. That is what's called the inverting input. And then we have a guy out here on the right-hand side, which is our output terminal. So this is a 3-terminal device. We have never analyzed a 3-terminal device before. In practice, if I pop back over to this guy right here, so the inverting input terminal is this guy right here. The non-inverting input terminal is this guy right here, and our output terminal is this guy over here. There's actually 4 other terminals for a practical op-amp that we may see, but they have nothing to do with the circuit analysis that we are going to do whatsoever. So I am choosing to ignore them. For those of you that go on to take circuits 2, either because you're an electrical engineer or you're working on an EE minor or something like that, we'll get into much greater detail about these other guys, but for the intents and purposes of circuits 1, we're just going to leave ourselves with these 3 terminals and call it a day. Okay. So what an operational amplifier does is it applies mathematical operations to electrical signals. Those mathematical operations can be things like addition, subtraction, integration, differentiation. With multiple op-amps, we can do multiplication or mixing, and therefore also division. So an operational amplifier, its purpose is to do math effectively on signals. So for our ideal operational amplifier, which is what we're going to be dealing with, where we only have to care about these 3 terminals, there are 2 very specific rules that we need to follow. And if we follow these rules, our circuit analysis will actually be fairly straightforward. Our first rule is that there is no potential difference between the input terminals. Another way of thinking about this, so if I identified the voltage present at the non-inverting input terminal, the nodal voltage there as V plus, and the nodal voltage at the inverting input terminal as V minus, then rule number 1 simply states that V plus must be identical to V minus. My second rule is that no current can flow into or out of the input terminals. So that means that I can say that I have a current, I'm going to call it I minus, and that must be 0 amps. And there might be a current as here, as well here, I plus, which I can say by definition must be 0 amps. So I'd like to talk for a moment about why these rules are valid for op amps. Okay. So if we look at this data sheet thing and we scroll way back to the beginning for the, let's see, not the operating conditions, electrical characteristics, I think. There we go, yeah. So the reason that no current can flow into or out of the input terminals, rule 2, arises from the fact that the input resistance of an op amp, or the Thevenin resistance seen looking into the pair of input terminals, is 2 mega ohms. Okay. So in this class, we've been dealing with resistors typically of the size of ohms to kilo ohms, never anything on the order of mega ohms. Mega ohms would be literally 1,000 times larger than the largest resistor that we've dealt with in this class to this point. And as long as we are biasing our op amps or using resistors that are of the value of, say, kilo ohms in an op amp, we can make that assumption that effectively no current will flow into the into or out of the input terminals. Now, the voltage present at the non-inverting input terminal being equal to the voltage present at the inverting input terminal is a consequence of this guy right here, what's called the large signal differential voltage amplification, which we can see has a typical value of 200 volts per millivolt, which in another way would be saying 200,000. So our differential voltage gain is extremely high. And as a consequence of the negative feedback that we're going to employ, which I'm going to talk about in a little bit, that causes the difference in the input signals to be incredibly small, and which gives us op amp rule number 1. And then the extremely large input resistance is where op amp rule number 2 comes from. So I've mentioned the concept of negative feedback, and so now I'm going to explain what that is with regards to an op amp. All of the circuits that we are going to be analyzing in this class will have one common thing happening. So I might have an op amp circuit like so. I'm going to choose to draw it slightly different. I'm going to put the minus sign on top and the plus sign on bottom. I'm perfectly able to do that. That just means that my inverting input terminal is on top now, and my non-inverting input terminal is on bottom. So all of the circuits that we are going to deal with in this class are going to have what's called negative feedback. And so that means that there will be a resistor or a wire or a capacitor or an inductor when we get into those types of circuits that connects the output terminal to the inverting input terminal. So this guy right here is what we would call a feedback resistor. And again, negative feedback means that there is a feedback path from the output to the inverting input terminal. All right, so let's look at some circuits. And I'm going to expect some help from you guys in analyzing these, okay? So I'm going to start. I'm going to draw my op amp. And we're going to talk our way through how we are going to solve these guys. Okay. So this is an op amp circuit. All right. We have some input signal, which in this case happens to be a 6.8 milliamp current, flows into the op amp circuit as a whole, and we are trying to determine the output voltage. All right. So we are going to do this, and we're going to solve pretty much all op amp circuits in this class using a very specific formula. All right. So the first thing that we are going to do is determine the voltage at the non-inverting input terminal. So that would be the voltage V plus, and I'm going to label it right here. All right. So who among you can tell me what this voltage is?
Will it be based on Ohm's law, multiplying the 6.8 milliamps by the 3.5 kilo ohms?
Will have nothing to do with that. I'm going to redraw this symbol real quick. So I'm specifically asking for the voltage at that node right here.
0.
0. So the non-inverting input terminal has a nodal voltage of 0 volts because it is tied directly to ground. Absolutely correct. That is step 1. Step 2 is apply rule number 1 to get V minus. So this is our voltage V minus. Op amp rule number 1 tells us that V minus has to be exactly equal to V plus. So it is 0 volts. So even though that particular node is not physically connected to ground, it is behaving as if it were connected to ground because the difference between the difference in voltage between the input terminals must be equal to 0. Okay. Step 3 is apply rule number 2 and do KCL at the inverting input. All right. So applying rule number 2, what I mean by that is specifically noting that this current right here has to be 0 amps. So if I write a KCL expression at this node, I can see that 6.8 milliamps is flowing in. And that same current of 6.8 milliamps must also be flowing through that feedback resistor because it has no other path to take. So I can say that 6.8 milliamps, the current flowing into that node, is the same as V minus V out divided by 3.5 kiloohms. Right? So that is just a simple nodal analysis or KCL expression at that node. All right. Excuse me. So V minus is where that current through the feedback resistor is starting from. The V out is the node at which the current ends up, and I divide by the resistor value. So that's just me using Ohm's law like I would do to express the current through a resistor in literally any problem I was attempting to do nodal analysis on. Excuse me. Since we know that V minus is 0 volts, I can just replace this with 0 volts. And now we have one equation, one unknown, and we can solve. V out is going to be negative 6.8 milliamps times 3.5 kiloohms. I don't have a calculator handy, so let me use my phone. Negative 23.8 volts. So let me ask you guys a question. How difficult was this analysis?
Not difficult.
Not very.
Yeah, all three, if we do these 3 steps in this order every time, you will be able to solve for every single circuit that we are going to deal with involving op amps in this class. Some of your peers and upperclassmen who have taken this class before might say, oh, op amps seem so difficult, blah, blah, blah. It is literally this over and over and over again. It doesn't matter how gnarly I make it look. These 3 steps and you're good to go. All right, let's do another problem. And I'm gonna let you guys take the wheel more so. So this guy is gonna be very similar, but with one fundamental difference. All right. Step 1, who can tell me what the voltage V plus is?
5 volts.
5 volts. So I'm going to label that here. 2. Who can tell me what the voltage V minus is? Still 5 volts, absolutely correct. So V minus is equal to V plus is 5 volts. So we know what this voltage here is. Step 3, we write our Kirchhoff's current law equation. What is that KCL equation going to be?
Then 9 milliamps is equal to 5 minus V out over 3 kilo ohms.
Kilo ohms. So we now have enough information to solve for V out. So solve for it.
I got V out is equal to negative 22 volts.
Absolutely correct. Boom. You have just analyzed an op-amp circuit effectively all by yourself. Let's do another one. So this one is going to technically involve one extra step, and we'll see why in a moment. So what is the voltage present at the non-inverting input terminal?
4 volts.
4 volts. So that means that this voltage right here is 4 volts. What is the voltage present at the inverting input terminal?
4 volt minus 2 volts.
Nope.
It has to be 4 volts, right?
Has to be 4 volts. So that means that this voltage right here is equal to 4 volts. Okay. Now, this is where things are going to be a little bit different. And so let me explain what I mean. Typically, our third step would be we write a KCL equation. But if we write a KCL equation, what would we come up with? Anybody have any thoughts here? So, for example, what I'm asking you in essence is, what is the current flowing through the 4 kilo ohm resistor? Let me redraw my current here, and I think it'll help answer the question. So the current flowing through the 4 kilo ohm resistor is the same as this current that is leaving the inverting input node and flowing through that loop. What is its value? Go back to op amp rule number 2.
0 amps.
0 amps, which means this current is 0 amps, okay? So our KCL expression doesn't give us anything but 0 is equal to 0 effectively, which isn't particularly helpful. So for this one, we can't really use that one. Like I say it's not helpful, but it is absolutely critical in solving this because we know now that the voltage drop over the 4 kilo ohm resistor has to be 0 volts. So how do you think we're going to be able to figure out what V out is? Any ideas?
Would that just make the V out equal to the V plus? So it would just be 4 volts?
Close. So there is still a 2-volt drop that's being forced by that voltage, that 2-volt voltage source. So since there's no current flowing around that loop, what we see is 4 volts minus 2 volts is equal to V out. And so let me explain exactly why that is, just real quick here. So I'm just going to draw a line out here. It doesn't particularly do anything. But we know that between this node and ground, there is 4 volts of potential, right? That's because of op amp rule number 1. So if we were to write a Kirchhoff's voltage law loop expression, we would have negative 4 volts plus 2 volts plus V out is equal to 0 because V out is the voltage at that output node with respect to ground. So we've started at ground and we have ended at ground. So that is a full KVL expression. Rearranging, we would see that V out is 4 volts minus 2 volts is equal to 2 volts. Does that make sense?
Can you explain it again?
Sure. So all of these voltages that we are dealing with, V plus and V minus, they are nodal voltages. They are measured with respect to ground, okay? So I'm saying we found what the voltage present at the non-inverting input terminal was right here, right? By inspection, we know that there's 4 volts applied at the non-inverting input terminal because there's a 4-volt source connected to it. Applying op amp rule number 1 tells us that the voltage at this node is also 4 volts, which is where we got this guy and where this guy came from. Excuse me. Now what we have had to do, because there is no current flowing in our circuit effectively, is instead of using KCL, which we use KCL to figure out that there's no voltage drop over the 4 kilo ohm resistor, we've written a Kirchhoff's voltage law equation. So the path that I'm following is this guy right here, okay? I see the negative polarity terminal of the 4 volts. Then I see the positive polarity terminal of a 2-volt source. I see my resistor, but I know that there's no voltage drop over it because there's no current flowing through it. And then I see the positive polarity terminal of the output voltage. So that's where my KVL equation came from. I started at ground, I ended at ground. So this is a full Kirchhoff's voltage law loop.
Dr. Hartman,
Yes, sir.
how can there be 2 volts and no like current? Like that just doesn't make sense to me.
So if you hold a battery in your hand, there is 1.5 volts of potential difference between the two terminals of the battery, and yet there's no current flowing through it.
Oh, okay. So it's just the potential there. It's not actually like nothing is happening. It's just that's the potential at that point.
It's not driving any current or anything like that, but the potential difference between the output node and ground is exactly 2 volts. That's a perfect way of thinking about it. Yeah, it's not pushing any current anywhere, but there's still a potential difference.
Okay. Thank you.
Mm-hmm. Any other questions on this one? This guy's a little tricky, I'm not gonna lie. I told you we could solve it, all of these circuits using 3 steps, and I forgot about this one where we have to add in a little bit more. But those three steps are still absolutely fundamental to figuring out what's going on here. We just have to infer a little bit more using our circuit analysis experience. All right. Here's another one that's tricky like that last one. This is one of my favorite questions to ask. Like legitimately, I may ask this very question on your next test. All right, so just to be clear here, I've gone and messed with things ever so slightly by putting my non-inverting input terminal back on top, my inverting input terminal on bottom. That doesn't change anything whatsoever with how we analyze the circuit. I can flip-flop those guys all I want and it changes absolutely nothing. All right, so here's our next circuit. What is the voltage present at the non-inverting input terminal?
0 volts.
All right. So we can say that V plus is equal to 0 volts. Perfect. What is the voltage present at the non-inverting, or excuse me, at the inverting input terminal?
0 volts.
All right. What's V out? So I'll ask you guys again. What value does this current flowing through the 7 ohm resistor or 7 kilo ohm resistor have to have?
0 amps.
0 amps. Okay. Which means there's no voltage drop over the 7 kilo ohm resistor. So what is V out?
Would it just be 0?
Absolutely right. So this guy tends to trip students up a little bit because a very reasonable question for you to ask is, where the hell does that 2 milliamps of current that's being supplied by that source go? So op-amp rule number 2 says explicitly that no current can flow into or out of the input terminals of an ideal op-amp, but it does not say anything about current flowing into or out of the output terminal of an op-amp. So effectively what this particular circuit is neglecting is the fact that there are connections to power supplies which have a path to ground for that current to flow through. Okay, so this one is intentionally tricky, but the answer is absolutely 0 volts for the exact same reason that the answer to the previous problem was 2 volts. If we do our Kirchhoff's voltage law equation and we write our path, so effectively we know that there is 0 volts here, 0 volt drop across here, and then back to ground across V out, we'll find that 0 plus 0 is equal to 0. So. All right. I don't want to do that one. Here's our last example problem for the day. This one is more in line with what I would ask you on an exam. All right. So this guy has lots of resistors and all that jazz, but we can absolutely still solve it correctly by using those 3 steps that I introduced at the beginning of the class. So, Sarah, are you still on Zoom?
Yeah.
I'm going to pick on you because I haven't heard you talking a little bit. What is the voltage present at the non-inverting input terminal? So this guy right here.
Wouldn't it be 0 because it's connected to ground with nothing in between?
So it isn't connected to ground with nothing in between. There's that 2 kilo ohm resistor there, right?
Nothing voltage outputting. So
Right.
might be wrong, but I do know there's a resistor there.
So there is a resistor there, but the voltage will still be 0 volts because there can't be any current flowing through the resistor.
Okay.
Right?
Yeah.
So, I mean, your assessment that there's no voltage source there is perfect as a perfectly valid reason, because we know for it to be 0 volts, because we know that no current can flow through that resistor. So that's perfectly fine.
Okay.
So 0 volts. All right. So somebody else, or Sarah, doesn't matter, tell me what voltage is going to be present here at the inverting input terminal.
Would it be 0?
It'd be 0.
Yep, 0 volts again. All right, and so now we write our KCL equation.
Mhm.
So somebody tell me how to do that. So what I would do, personally, I'm about to sneeze. I'm writing KCL at this node because that's my non-inverting input terminal node. So I would have this current this current and this current added together because I know for sure that this guy has to be 0 amps. So tell me what goes in my equation. Anybody have any thoughts? What's supposed to go into that KCL equation? I've literally told you what.
Don't we need to determine the current going through the 1 kilo ohm resistor, which will be the 2 volt divided by the 1 kilo ohm, which will be 2 amps for the first current going to the left?
So it won't be 2 volts. It'll be negative 2 volts. Right? So we're writing a KCL equation just like we were doing nodal analysis, right? So, and we're having the currents leave that node that I've circled in blue. So it would be whatever nodal voltage this is, which is 0 volts, minus 2 volts, divided by 1 kilo ohm. So that gives us our current flowing to the left through the 1 kilo ohm resistor. Does that make sense?
Yes.
Would you not need to worry about that 10 kilo ohm right there since V out or the V minus is 0 volts?
So technically you are correct. We do not need to worry about that guy, the 10 kilo ohm resistor at all, because we have 0 minus 0 over 10 kilo ohms. So it does not contribute anything. It is effectively shorted out. So we can absolutely skip that. I am going to put it in just for the sake of argument, but you're 100% correct that we don't need to by any stretch of the imagination. So the last thing that we have then is the current flowing up and to the right through the 5 kilo ohm resistor. So what's that going to be?
V minus V out over 5 kilo ohms.
So 0 volts minus V out over 5 kilo ohms is equal to 0. Rearrange this guy and solve. And I can tell you that V out is going to be negative 10 volts, but I'd like for you guys to verify it.
Negative 10 volts.
Negative 10 volts. So that is the most complicated circuit that we have dealt with in this class, at least regarding op amps thus far. And those 3 simple steps are all it took to solve this guy. So determining the, again, step 1 is determine the voltage at the non-inverting input terminal. Step 2 is to determine the voltage at the inverting input terminal using rule number 1. And then step 3 is apply rule number 2 and then do KCL. On your exam, all of the questions having anything to do with op amps, other than if I literally give you this exact question right here, will be able to be solved just using those 3 steps. No matter how utterly complicated and convoluted it looks like, you can solve them using those 3 steps.